Shredding popsicles.
Okay, well, as long as we're paying attention to Tuesday. Okay, so again, I don't know if the notes are going to help you, but if you want to take any notes, you're welcome to. I primarily want to just get some information out there, and then we can do some sample exercises of projectiles. And then whatever time we have, you can continue working on your lab over the next couple days. Okay, so two-dimensional motion. The critical thing in two-dimensional motion is we're dealing with a parabola. And we're dealing with a parabola because the acceleration in the vertical direction falls off with the square of time. So if you graph, you will, actually if you haven't already, if you graph displacement versus time in the x-axis, it's just going to go whoop, because it's constant. Velocity x-axis is constant because there's no acceleration changing the x motion, right? So the slope of the distance time curve or displacement time curve is velocity. Velocity is constant. Not zero, but constant. However, if you graph it versus dy, then what you get is either a half a parabola or a full parabola. If you throw it from the ground, you get a full parabola. And if you throw it from the top, you get half a parabola. And you get that parabola because, I should make this the right color. You get this parabola because dy equals 1/2 at squared. Again, if you want to put the VIT in there too, but it's the t squared that gives us our parabola. On the other hand, dx is just vxt because the velocity doesn't change. There's nothing to pull or push the velocity in the horizontal direction. Okay. How are we doing? Good so far? Yeah. All right. I haven't used a button in years. Okay, so quickly talk about vectors. Again, you had a little vector exercise earlier. A vector is something that has magnitude and direction. And the most important thing about two-dimensional motion when you have vectors is vectors that are perpendicular to each other do not interact with each other. Vectors that are perpendicular to each other do not interact with each other. And there you go. So if you got one-dimensional vector, you had the exercise about this. So this is like elementary school number line where you have a line going, arrow going that way, arrow going that way. The result is always found by putting them head to tail. So I'm going to take this one and put it up here, and I get that. Head to tail, the head of this one to the tail of this one, move it up here, and then that's the result. Similarly, if I take this one and set it up here, that's the result. And then you did number line. Remember number line in elementary school? That's one-dimensional vectors. Now, two-dimensional vectors are a lot more important. When you do two-dimensional vectors, you can still add them head to tail. That's called the graphical method of vector addition. So when you add vectors in the two-dimensional, you still add them head to tail. So there's a vector there, and there's a vector there. The animation's all screwed up. It's probably going to move later. But you can imagine this one goes here, you move it head to tail. The resultant is where you start, the tail of the first vector, and where you end, the head of the second vector. If you're clear with that, give me a thumbs up. Okay, so when you have two vectors, the two vectors you're adding are the yellow ones, you still add them head to tail. You can take this vector and move it up here, or you can take this vector and move it up here. Either way, the resultant is where you start, the butt of the first vector to the head of the second vector. Now, the important thing about vectors, and this actually is a testable point, is they have two properties we care about: magnitude and direction. We don't care about translation, which is why we can move around. We can take this vector and move it up here. We can translate it to the top of this vector. That doesn't change the vector. Vectors have only two attributes. They have magnitude, how long they are, and their angle or their direction with respect to an origin. Usually 0 degrees is that way. It'll be like 45. This will be like 210. Okay. Usually. You understand what I mean by to the origin, a zero origin? So if you had this angle, it would be like 45 degrees. And this would be like 210 degrees. Just 3. Nope. Right. Oh, okay. Here's another one.
Actually, no.
So imagine if you took this vector and placed it here.
Just root 3 over.
You would start at the end of here. It would go this way, this way. That's the result. Or you could take this vector, move it down here, and go this way, this way. That's the result. Or you can take this vector, move it down here, and you'd have go this way, and that would be the result. Maybe the animation is fixed eventually. Maybe one of these days. I'll fix the animations. Google Slides is giving me frustrations. What direction is the result of these two vectors going to look like? Yeah, probably straight up, right? You're just going to take this vector, add it to the top of this, and the result is like that. Or take this vector, add it up here, and the result is like that. Now that's the graphical method of vector addition, and it's handy when you want to figure out approximately what the resulting vector should look like. More valuable is breaking a vector into its components. This is not important. Here. So most important, oh yeah, vector subtraction. When you do vector subtraction, if you ever need to subtract vectors, which you might have to, you just add their negative. And a negative vector is exactly like a negative number. Has the same magnitude, but the opposite direction. So, for instance, if this vector is q, this vector is negative q. Same magnitude, opposite direction. Just like a number. The magnitude of 4 and negative 4 is the same, it's just their sign moving. Okay, here we are. Okay, so take a couple minutes, and with these vectors, A and B, again, if that's A, that's negative A. If that's B, that's negative B. Calculate these guys. Just sketch it on your notes or paper or whatever. What would it look like for each of these vector combinations?
I think it's longer than B.
Again, feel free to show your number, but you don't. Work together, get older.
What do you think?
Why is 9/11 a big thing?
What do you mean? So I'm missing 3 times. What do you think? Just wait.
Yeah. is longer than B, so it'll still be.
Keeps adding
This
together.
Yeah.
That accounts for it.
What's 2B like?
Longer.
Show me with you right now.
Do we need more time or are you good? Good, good, good. All right, so 2A, if that's A,
That's true.
that's another A. So this, actually I want to do for color. This, oh, here we go, is 2A. And then if that's B, there's another B. So this one would be 2B. Comfortable with this?
Yeah.
All right. So then A plus B, let's erase those. There we go. So if that's A, one more back. There we go. If that's A and that's B, then this is A plus B.
Yeah.
And then A minus B. A minus B is the same as A plus a negative B. So if that's A, and this is negative B, then this is A plus a negative B or A minus B. Are we comfortable so far?
Yeah.
Is your work looking like mine? More or less? Okay. So which of these vectors is or are identical? Which of these vector sets are identical?
A minus B, negative B plus A.
A minus B. Oh, A minus B.
There are a lot that are identical.
A minus B and
Negative B plus A.
negative B. Oops.
Bottom left.
There we are. Negative B plus A. Because in this case, you're adding a positive A to the negative B, positive A to a negative B. Is there another one?
Negative B minus A. And negative A plus negative B.
Negative A plus negative B. You're adding a negative A and a negative B. And here you're adding a negative A and a negative B. Is that what you got? Do those vectors look about the same on your paper?
Yeah.
All right, cool. Any questions before we move on to actual vector stuff that we can actually play with? Moving on. All right, so that's vector addition. Again, graphical vector addition. When we need to actually get vectors quantitatively added, we have to break them into their components. And that's going to require a little bit of trig. Remember the triangle math activity that you were asked to do, or you saw, or you'll do tonight? So if you don't remember your trig, that's fine. It basically boils down to this. You have sine, cosine, and tangent. That's all you need. You just need sine, cosine, and tangent, and their inverses. A tangent, A sine, A cosine, or sine to the -1, cosine to the -1, and tangent to the -1, whatever they call it, depending on what textbook you're reading. So, and again, if you like the SOHCAHTOA, you probably know all about it. Most important, the way I like to think about it is sine means opposite, because the word sinister comes from the same place where we get sine. Sine means opposite or against. So somebody who is sinister is opposite you. Like, he's opposite, he's sinister. So sine is opposite. And yeah, there you go. And you can do your SOHCAHTOA all over the place if you want. Okay, so we generally give the magnitude of a vector a certain value, and then we use cosine to calculate the x component and sine to calculate the y component. So if you had the vector m here, its xness, its x component is m cosine theta, because cosine is the adjacent right here. We just translate it up. I can take this vector and translate it down, because translating a vector doesn't change anything. So the x-ness of that vector is m cosine theta, and the y-ness of that vector is m sine theta. That's going to be really important because we can come back to it. And what we're going to do with it, and specifically in projectiles, is we're going to have a vector v, and we want to know how much of that v is vx, and how much of that v is vy. So we break a velocity into a vector vy and vx. Vy is going to be v sine theta, and vx is going to be v cosine theta. And theta is the angle measured to the zero. Now you also have to realize this is super, 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 super important. Theta starts at 0, goes to 90, goes to 180, goes to 270, and then back to 0 again. Your computer that you have in your hands or in your cell phone does not know the difference between things in quadrant 1 and things in quadrant 3. And it doesn't know the difference between things in quadrant 2 and things in quadrant 4. Let me show what I mean. So this is plus x plus y. This is negative x plus y. This is negative x, negative y. And this is negative x plus y. So far, so good?
Isn't that plus x negative y?
Like I said, this is plus x, negative y. Okay, are we good so far? All right. When we want to get an angle, we're going to use tangent, right? So let's say I have a vector. You ready? Well, actually, just give me a vector magnitude. Any vector magnitude.
5 plus 5
How much?
plus 5.
Plus 5. Okay, so I got a vector that has a magnitude of 5. And I should have waited until it got me an angle. Give me an angle.
45 degrees.
I'm going to make it easy on me. Okay, so 45 degrees. So in determining what those magnitudes are, we can look at that and say, all right, I have a vector that looks like that. This vector has some value of x and some value of y. So go ahead and give me what those x and y values are. Let's go ahead and take your calculator, bang them down. Just, what are those x and y values?
No.
I know what they are by heart, but I want you to know that.
It's root 2 over 2.
No, it's still a
Oh wait, it's
right
5.
triangle.
That's not
Right.
Why didn't we say magnitude of 1?
So
Yeah, it's not a 3.5. How much is it? Anyone?
It's not a 3.5?
no,
Yeah, because it's a
45,
special.
40,
It's a-
45, 45, 90.
So
Yeah, so what is
Root
the
2 times
magnitude of the
Yeah.
legs of
Five.
x and y?
5 root 2.
Which is?
I got 3.53.
7.0.
Guys, it's like
Well, now I'm really glad we did this little activity. You just go 5. Oh, please make sure your calculator is in degrees and not radians.
it should be 7.07.
Oh.
Uh-huh.
Is it 2.63?
Wait,
It is
what am I doing
2.63.
Yeah.
The
1,000 radians, my bad.
exactly.
Is
So,
it 2 times the square root of
you guys are
Oh, it's
your math
wait.
teachers are killing me here.
Way over.
It's
All you
2
do
times
is go make sure you're in degrees and go
4.47.
5
No, it's 3.
cosine 45. Enter 3.53.
Yeah.
Oh.
And if you have a numbers calculator, it actually puts it as 5 root 2
Oh.
over 2.
No, it's you divide by root 2.
Yeah.
If you divide by root 2.
Wow. Okay, so this is 3.5, and this is 3.5. Cool so far?
Right here, I got it.
3.53 or whatever. No, we're really glad we did this. So it's really important that your calculator is in degrees. And the reason that is while we'll use radians in the future when we get to rotational motion, we never do any math in radians. All the math is going to happen in degrees. Does that make sense?
Yeah.
So we'll talk about like, it's pi, it's 2 pi. And we'll talk about what a radian is, but that's for the future. And when we do any math with degrees or angles, it's always going to be degrees. All right, so 3.5, 3.5. Now, let's do this. Okay, Now, if I had an angle, I can use that angle to get sine, cosine, and even tangent, right? If I needed an angle, I would use the reverse. So if you know that the angle in there is the inverse tangent of y over x, opposite over adjacent.
Yeah.
Okay. For those who are like, I remember we did math like that. Okay. So when you do the inverse tangent of 3.5 over 3.5, what do you get?
45 degrees.
Yeah. If you do the inverse tangent of 3.5 over 3.5,
Should've.
you get 45 degrees.
Pi over.
Let's use the negative of that vector. The negative of that vector has the same 5-degree magnitude, but the angle is 225.
Yeah.
225 degrees. So what is this y-ness and this x-ness at 5 sine 225 and sine negative, or 5 cosine 225 and sine 225?
Negative 3.5 for both.
It's negative 3.5 and negative 3.5. Right?
Which is the exact.
We use the angle of 225. Okay, now here's where the fun, this is the punchline. What is the tangent, inverse tangent of negative 3.5 over negative 3.5?
That just cuts not to 1.
45 degrees.
45 degrees.
Pi over 4.
So if you don't know where your vector is, your calculator will give you the wrong answer. Because it does not know the difference between quadrant 1 and 3 or 2 and 4. Do you see why it's important to add vectors graphically first?
Mhm.
Yes.
It's like if you break down two vectors into those parts, you just add them together like they're linear again.
Yeah.
Like the x and y.
Yeah, if I wanted to add this vector, let's call this vector green to vector blue. I would add the y of vector blue to the y of vector green, and the x of vector blue to the x of vector green, and it shouldn't surprise nobody that the result is 0. Speaking of adding vectors together, any questions before we move forward? Like I said, speaking out of adding vectors together, this is what we're going to do now. Okay. Again, it's going to come up with all the vectors at the end, but whatever. Okay, come on, you can do it. There they are. Okay, so here are 3 vectors, 1, 2, and 3. What do you want to add together? 1 and 2, 2 and 3, or 1 and 3?
1 and 3.
Add 1 and 3. So this is what you're going to do. You're going to first sketch 1 and 3 and add them graphically. Then you're going to break 1 into its x-ness and its y-ness, and you're going to break 3 into its x-ness and its y-ness. Then you're going to add the x's together, add the y's together, use Pythagorean to find the magnitude, and inverse tangent to find the angle. Go for it. Feel free to work with a partner, and somebody bring Valentina into the conversation too if she needs help. Because Autumn's missing today.
Yeah, so I'm gonna find the x and y.
We're doing just 1 and 3, right?
So this should be 2.5, right?
My code expired. Give me a new one.
Just 1 and 3, right?
9.66.
Just 1 and 3.
So I got 9.68.
Right? So 10. So now I'm solving 300 degrees, right?
Negative 1.71. And then negative 1. Please add this to this.
This? So we're searching for this, since this is the adjacent side.
Minus
We do
1.7.
Cosine.
96 here, x.
We do the cosine of
And
15.
y
is equivalent to
2.59 minus 1.7.
So then leave this.
Minus 200.
cosine of 15 x over 10.
Oh, I thought you said x to the 10.
Oh, x over 10.
What? This.
Is this 0?
So output then?
Make sure you're
How much would be to math?
opposite of
Is it
this.
what?
Opposite. Inverse. Did you get?
Oh.
79.
Switching the x vector is 9.6.
Alright.
So
That's good.
number solve for y. Y is equation equal to the sine of 15, which is going to be x over 10 base. So we have sine.
What's 2.6?
What?
2.58. Yes.
You find, number one and number three.
Yep.
So what do you have for number one?
I got 9.7 for
Down here.
9.7,
Yeah.
2.6, yeah.
and then
It looks like it's hard.
9.7
Yeah, good.
Negative 1.7
Yeah.
and negative 1.7.
Yeah.
Is that on PC?
The second
And then it should be,
Hi.
So the angle would be 4 then.
But you can, yeah. You can connect it.
So we're gonna have 3. Okay, so
You see like arrows are gonna be
Those general thing.
You see like arrow keys.
right, so our angle was
So it's like 100.
Oh, and you add the x and the y.
so this is that's x, y. Cosine of 200 is equal to x over 5, and the sine of 200 equal to
I mean, yeah, if you have negative angle deviation for the rest of them.
it should be magnitude of,
You know what, I remember the grade term that has to do with.
Some people say
It seems like
the resulting angle, that's the issue.
here.
So
I know lawmaker.
I know it's in the fourth quadrant.
you're making
So now I need to
like
find
This is where they're confused.
that using 10.
Yeah.
So I'm saying is
on the graph, the angle would be 20 degrees.
Oh, inverse tangent, that's what it is.
Just use
So
200 and use the negative immediately. So you don't have to, so you don't actually forget the negative.
Would you forget the negative? Yeah.
Negative 1.7
golden.
just y. I was add these two numbers together. So negative 4.7 plus
I don't know if I did inverse tangent, but whatever.
negative 1.71 plus 2.59. How we do it?
How do I even?
What we answer? I don't know. Let me write the answer. How much was?
John's gonna love this chapter. All about these.
And the magnitude,
Is incorrect.
Yeah.
0.88, so
well, I'm going to,
plus 0.88,
so that would be,
and the magnitude is 5.03.
On market-based musical economy.
What's it? Okay, so this is all that. What did you guys get for X and Y for the?
4.96 and 0.8. 0.88.
X.
In what?
So what is 10 cosine 15?
We're doing 1 and 3.
Yeah.
9.66.
I got that.
Okay. And what is 10 sine 15?
2.9.
2.5?
9.
2.6? Okay. So are we good so far? Are these the components you got?
Yeah.
So what this means is vector 1 has 9.7 units of xness and 2.6 units of yness. Right?
Yeah.
Okay. And then what is 5 cosine 200?
Negative 4.7.
4.7?
Yeah.
4.7? Okay. And what is 5 sine 200?
Negative 1.7.
1.7?
Yeah.
Okay. So we're saying vector 3
See, it's small.
has negative 4.7 units of xness and negative 1.9 or 1.7 units of yness, right? So when you add them together, you're going to take the x is going to be your 9.7 and you're going to add it to your negative 4.7, right? We're all good so far? And then the y is going to be your 2.6 plus your negative 1.7.
Beginning the motor to build number for that. I can have to run in the motor.
Are we comfortable with this? Now again, this is just magnitude. We don't know what the angle is, we just know the magnitude. So this is going to be hopefully 5.0 and looks like 0.9? Is that about right? So we're going to look at this and say, all right, the resultant vector is going to do this. From the start to the end. And our numbers tell us that our resultant should have 5.0 xness and 0.9 yness. Capiche? And to get the actual value, you're going to use the Pythagorean theorem of 5.0 square root of 5.0 squared plus 0.9 squared. And the angle, you're going to use the inverse tangent of 5.0 over 0.9. So what is our magnitude?
I used to.
5.08.
5.08.
So 5.1.
So 5.1. And what is our resultant angle?
It was 79.9.
79, really?
Yeah.
Wow, I kind of botched that one, didn't I? Botched that diagram. I'll take your word for it. 79 degrees.
Yeah.
Nope, it's backwards. It's y over x, not x over y. I got this part wrong. So the y is 0.9 and 5.0. There we go. Y over x, y over x, y over x, y over x.
It's 10.2.
10/2, that's much better. Okay. 10 degrees. So this here is 10 degrees, and this here is 5.0. So that's how you add vectors mathematically. You break them into their pieces, add the pieces, put them back together. So you have a sim, or basically you have another like 15 minutes to work on your sim, and then we're gonna do an exercise with this tomorrow, and then you can finish this sim tomorrow. Questions? Yes,
What's the R?
resultant.
Okay.
It's just the magnitude of the resultant. And that's the word we use. We use components and resultants. We break vectors into their components. We add the components to get the resultant. Questions? Okay. It is unlocked, right? The vector fed addition sim
I think so.
and the graphical vector addition worksheet. Okay, so go ahead and use that with the remainder of your time. And then we'll finish vectors tomorrow, and you can use the remainder of time to finish your sim if you need it. And bye, Autumn. Hope you got something out of this. And